In the previous video, we started looking at this concept of atomic orbitals, and I totally get that at first this is really wackadoo and seems kind of crazy, but eventually it explains some things that maybe you've been told from a previous science class and kind of always wondered, why is it like that? And so this is the concept of electrons not just flying around in a circular orbit, but they're contained in these three-dimensional regions called orbitals. And so the first energy level is a small energy level right next to the nucleus, and it only has one orbital, just this one s. And so the 1 stands for the first energy level, and the s stands for spherical. It's a spherical region. It's like a three-dimensional bubble around the nucleus where you could find up to 2 electrons. Every energy level has an s orbital. It's just that they get a little bigger. So the 2s orbital is also a spherical region around the nucleus. It's just that the 2 electrons can be a little bit farther from the nucleus. Once you get to the second energy level, you'll also find the p orbitals. So first energy level only has an s. It's just too small for any other orbitals. Second energy level will have a 2s, and you'll find these p orbitals. They're my favorites. There are 3 of them. The p's have more energy than the s orbital, but the 3 p orbitals themselves are all equal energy. The difference is just that they lie on a little different axis in space. Their orientation is a little bit different. And so sometimes we use the letters x, y, z to show the axis. They still hold 2 electrons. Altogether, the p orbitals can take on a maximum of 6, 2 in each of the 3 p orbitals. But then that's it for the second energy level. So the first has an s, the second has an s, and the 3 p's. Then when you get to the third energy level, there would be an s. It's just even bigger than a 2s. Still holds 2 electrons. Then you'd have the 3 p orbitals. They're still dumbbell shaped. They still hold 2 electrons each. There'd still be 3 of them, so you could have a maximum of 6 electrons in the 3 p orbitals. They're a little bigger than the 2 p orbitals. And then you find the d orbitals. The d orbitals don't show up until the third energy level. They're a little bigger. They've got 4 lobes, and they're higher in energy, so you won't find these in the first or the second energy level. And when you find them, there will be 5 of them. 5 equal energy. They just, again, lie on a little different plane in space. But it's like 4 little bubbly regions where you could still find a maximum of 2 electrons each. So the D's, if they're all filled, would hold a maximum of 10 electrons. Ah, interesting. And there's still the chance that the electrons could be in any of those 4 regions of the d orbital. It's just that this orbital gives us a shape, a 3-dimensional shape, where we have a high probability of finding up to 2 electrons. Then that would be it for the third energy level. There'd be an s orbital, there'd be 3 p orbitals, and then there would be the 5 d orbitals. Then if you were in the fourth energy level, you'd have a 4s orbital. That'd be a really big sphere. You'd have the 4 p's. They would just be bigger dumbbell shaped. You'd have 4 d orbitals. They would still be these cloverleaf shapes. They're just bigger. And the fourth energy level is where you would find the f orbitals, which are kind of crazy. And they've got 8 lobes and super high energy. They still hold a maximum of 2 electrons each. So if there are 7 of them, they could all hold a total of 14, like all together. Craziness. That's what they're trying to explain down at the bottom of this model. From the previous page, each shell, I call them energy levels, but each shell has a certain number of subshells. The subshells are like the individual orbitals. So the first shell is like the first energy level, and it only has a 1s orbital. The second shell, or the second energy level, has an s, and it has the p's. The third energy level has the s's, p's, and d's. The fourth energy level has the s's, p's, d's, and f's. Oh my gosh. And then they're kind of showing us like how many orbitals there are for each of those different subshells. So anytime you have an s orbital, there will only be one. Anytime you have a p orbital, there will only be 3. There will be 5 d's, and there'll be 7 f's. Okay, so let's see if you're catching on to this a little bit. Do you remember how at one point the teachers told you that you can have 2 electrons in the first energy level? And maybe at the time you were like, well, I wonder why. Well, here's the why. It's because the first energy level only has 1 orbital available. And these little boxes here are super teeny tiny. I'll see if I can make this really, really skinny. Maybe. And I'm going to go for like a bright color. I'm going to go for like yellow. Okay, so when we have these boxes that represent an orbital, the boxes don't show the real shape because that would get crazy to draw, and you will never ever have to draw orbitals. Often in these boxes we put 2 arrows to show 2 electrons spinning opposite. Actually, maybe not yellow. Let's go like red. Red might be nice and bright. Well, if I were to like put 2 arrows, I guess that's kind of like 2 arrows in this box, spinning opposite. That represents the 2 electrons in the first energy level. It's the only orbital. There's only a 1s orbital in the first energy level. Oh. Well, I bet at one point you were told that the second energy level can hold 8 electrons. Well, it's because of the available orbitals. The second energy level would start with an s. So you'd have the 2s. Oh. And there'd be like 2 electrons in the box. And then, oh my gosh, this is going to be kind of tricky, but 1, 2, 3, 4, 5, 6. Then you'd have the 3 p orbitals. The p orbitals always come in groups of 3. And they can each hold 2 electrons. So in the second energy level, there's 2 electrons coming from the 2s orbital, and there's 6 electrons coming from the 2p orbitals. That adds up to 8. That's why there's 8 electrons in the second energy level. It's because of the available orbitals. At one point, you were probably told that the third energy level can hold 18 electrons. It's because of the available orbitals. So in the third energy level, there would be an s. The s can hold 2 electrons. There would be the p's. 1, 2, 3, 4, 5, 6. Oh boy. And again, these arrows are supposed to show the electrons and the fact that they kind of spin opposite when you put them together in an orbital. And the third energy level is the first time where you find d orbitals. When you find d's, there are 5 of them. 1, 2, 3, 4, 5, 6, 7, oh my gosh, 8, 9, 10. Oh yeah, because the d orbitals can each hold 2 electrons max. And so if there are 5 orbitals, that's 10. 18, it adds up to 18. There's 2 from the s, plus 6 from the p, plus 10 electrons from the d's. That's why there's 18 electrons in the third energy level. It's because of the available orbitals. Oh my gosh! Now, if you went this far in a former science class, maybe you would have learned that the fourth energy level can hold a maximum of 32 electrons. Oh yeah, it's because of the available orbitals. This is a lot of electrons. But let's do this. That if there were electrons, the 4s would hold 2 electrons. If the p orbitals were filled with 2 electrons each, that'd be a maximum of 6. There are 5 d orbitals. They each hold 2 for a total of 10. And then there are 7 f orbitals that can each hold 2 for a total of 14. So rather than drawing 32 tiny arrows that I can barely fit in these boxes, are you for real? It adds up to 32. Isn't that crazy? So this Schrodinger math, these crazy mathematical equations that came up with these shapes and sizes and how many orbitals, and we don't have to get into any of that. But evidence from his models is kind of relevant in that it tells us how many electrons we can fit in each energy level. And why do we care? Well, eventually, we really, really care about the electron structure, because when I have 2 atoms and I want to see if they'll interact with one another, will they bond with one another, will they have a chemical reaction? If you bring 2 atoms close to each other, what's the first 2 things to interact? It's the electron cloud. That's what's on the outside of the atom. So we really want to get a model, a good model of the electron structure, because that's going to help us predict bonding and chemical reactions. That stuff's really cool. Okay, so here we can kind of use this orbital stuff to explain how many electrons are available in each orbital. Now, I'll show you a video that's like an animated video that maybe does a better job of showing the fact that these orbitals don't just like fly in a circle. We have to picture that the nucleus is in the middle. It's just, again, that the nucleus is crazy, crazy tiny compared to the size of the electron cloud. We've just got one nucleus. And it's not that these electrons, or these orbitals, like, it's not like bubbles that fly around the nucleus. They're all kind of superimposed on the nucleus. They all kind of overlap each other in this 3-dimensional array of orbitals. It gets kind of wacky. Can you kind of see this? Let's see if I can change the color. Can you kind of see this like small spherical region around the nucleus? That's like the 1s orbital. Then there's like a larger spherical region. That's the 2s. And then even larger yet, there'd be a spherical region. Here's the 3s. And so on. And again, it's just that these orbitals are kind of superimposed or overlap one another. But if I'm an orbital in the 3s, or if I'm an electron in a 3s orbital, on average, I can be a lot farther from the nucleus. And it's kind of shown by the shading. I don't know if you can kind of tell that, like in the 3s orbital, it's darkest around the outside. Well, that's the best probability of finding your electrons. And it might be a little lighter toward the inside, and that would just mean that the electrons aren't as likely to be closer to the nucleus in, say, a 3s orbital. Now this picture it's hard to kind of see the p orbitals, but they're in there, and I'll show you an animated version of this that I think does a little bit better job of showing how these orbitals all overlap one another. But I like the way this kind of shows the s orbitals, that they are all like superimposed on the same nucleus. All right, so here then is another way of looking at how these orbitals connect to each other and how they relate to one another. In a given shell or energy level, the orbitals in each subshell have the same energy. Okay, so subshell just referring to like the different types of orbitals, and we've kind of mentioned that. So that's kind of like here, once you have p orbitals, they're all at the same energy level. And so they're kind of showing like 3 boxes, like 3 green boxes that are all equal to each other. They're all at the same energy level. Same thing with D's and F's, that all the D's in a particular energy level are the same energy. So all 5 of the 3D orbitals are equal energy. Now the 4D orbitals have more energy and the 5D orbitals have more energy, but within a particular energy level, they're the same. And that would also be true of the F orbitals. The 7 F orbitals in the 4th energy level all have the same amount of energy, but the 5f orbitals would be higher. Now, when we fill electrons in orbitals, we always fill lowest energy to highest energy. So in general, we fill S's, then P's, then D's, then F's. Lowest energy to highest energy. Now, there are times when the pattern might be maybe not exactly what we expect. It works really good for about the first 18 electrons. And then the wheels fall off just a teeny bit. This model is fine. I've got a way better model that I can show you soon that helps us to understand the order that the orbitals fill. Like, how do the electrons fill the orbitals? But this one's not awful. It's trying to show that we would fill these orbitals in order of increasing energy. And so we're supposed to kind of follow this zigzag line to go from the lowest energy orbital to the highest energy orbital. And so when number 26 says to use this model to list the subshells that hold the 25 electrons in a manganese atom in order of increasing energy. Okay, well, first, if I do look at the periodic table, manganese is element number 25. So a neutral atom should have 25 electrons. Okay, well, let's try filling these orbitals. I'm going to fill them with arrows. I'll try the best I can. And so we would always start with the lowest energy orbital, which is the 1s. So the 1s orbital would get filled with 2 electrons, and they spin opposite. So I'll show them with oppositely pointing arrows. And then that's it for the first energy level. So then you'd move on to the second energy level, always starting with the s, the lowest energy orbital. This would get 2 electrons. Then I would go to the next available orbital, which would be the p's. The p's can have up to 6. Now, I'm going to show you a rule here. It's called Huns Rule. Huns Rule states this: fill equal energy orbitals with 1 electron first before pairing. Okay, so right now you're like, what? Huns Rule makes total sense. It says to fill equal energy orbitals. And by equal energy orbitals, we're talking like P's, D's, and F's. So this rule applies to P's, D's, and F's. When you're in an energy level and there's more than one of a particular orbital and they're all equal energy, you're supposed to fill them with 1 electron first, and then if you have to, we'll go back and pair them. It's like this. So let's say I have 3 bedrooms and I have 3 kids. Well, of course I'm going to try to give each kid their own bedroom. If I don't have to pair them together, why would I? They're just going to fight with each other, right? Well, same thing with electrons. Electrons are all negative, and like charges repel. So I don't want to have to put 2 electrons in the same orbital if I don't have to. It minimizes repulsion. Minimize repulsion. Electrons are all negative, and we try to spread them out if possible. But this has to be equal energy orbitals. So for example, like when I get to the 2 p orbitals and I'm filling them with electrons, we're going to fill them with 1 electron first. I don't want these electrons to fight with each other, just like I don't want my kids to fight with each other. So if I can put them in their own room, I'm going to do it. Well, now we're trying to fill up to 25 electrons here. And the rule is also that you cannot move on to higher energy orbitals until you completely fill the lower orbitals. So, sorry, before I can move on to the third energy level, I'm going to have to go back and pair these. So right now I've got 2, 4, 6, 8, 10. I got to keep going. So we're going to hop to the third energy level. We'd start with an S. 1, 2. Then we're going to go to the P. I'm going to go 1, 2, 3. I go 1 electron at a time. But obviously that only gets me to what, like 15? I'm going to have to go back and pair them. Sorry. Mom just had triplets. Y'all got to share. Okay, so we keep going. The third energy level is supposed to have d orbitals available, but there's a little discrepancy. And I've got a great way to help you remember this, but I'll show it to you in another video. We need a periodic table. Right now I'm at 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. I need to go to 25. What you would think then after the 3p, you would go to the 3d. But in this model, they've got the 4s first. So it looks like I should go 4s, that holds 2. Okay, that gets me to 20, but I need to go to 25. So once I get to the next available orbital in this model, it looks like now it's the 3d. And then Huns Rule would also apply. I'm at 20, I need 25. Well, these d's are equal energy, so I should fill them 1 electron at a time. I've got 5 kids, I've got 5 rooms. Everyone gets their own. And that is the most stable arrangement of 5 electrons with 5 available orbitals. It minimizes the repulsion. I don't have to pair anybody. There's the 25 electrons in the manganese atom. The one thing that's a little goofy is this. Now, I wasn't expecting this right here. I thought after the 3p I'd go to the 3d, and then I'd go to the fourth energy level for the 4s, the 4p, the 4d. That 4s and the 3d are a little bit out of order. And it's just this, that we fill orbitals lowest energy to highest energy. Usually that goes SPDF. But there are a few times when it doesn't. Here's a way that I think of it. Okay, so pretend there's a boxing match. There's a boxing match, and in one corner of the ring, there's one guy. He's really big. He's really big. But he's kind of slow. He's kind of low energy. So his claim to fame is just that he's big. In the other corner of the ring are 5 guys. They're a little bit smaller, but their claim to fame is that there are 5 of them, and they're higher energy. So it's like they just had Mountain Dew and Pixie Sticks for breakfast, and they're ready for this battle. And so then you put these guys against each other, and you say, who's going to win? The one big guy, who's a little bit slow and low energy, versus the 5 little guys that are really high energy. And the winner is the 5 guys. The 5 guys win the battle. It's kind of like the battle between the 4s and the 3d. Yeah, 4s, well, 4 would mean that it's in the 4th energy level. That's a bigger orbital. On average, the electrons can be farther from the nucleus in the 4s, but it's an s orbital. There's only one, and it's a lower energy orbital. Versus the d's. Well, 3rd energy level means a little bit smaller orbitals that are a little bit closer to the nucleus, but there are 5 of them. And a d orbital is a lot higher energy orbital than an s. And so when you put all factors together, and we really do fill orbitals overall lowest energy to high, the 4s is kind of the loser of the battle. It turns out that the 4s actually carries a little bit less energy than the 5 3D orbitals. And so we do fill them low energy to high energy, and so sometimes they're a little bit out of order. Oh God. But don't worry about it. I've got a really great way for you to remember any of these little discrepancies. Don't worry about memorizing it. I've got a really awesome method that'll help you out in the future.